Good afternoon. My name is James Lim, and I'm going to be talking about cold form steel design of structures in New Zealand. This presentation has been prepared with one of my PhD students, Puya Paladi, and I'd just like to thank him for that. So, before we begin, I'll explain to you what cold form steel is, just in case you've not come across this building material before. So right up here you can see the normal stress strain curve for hot rolled steel or heavy steel. You can see that the stress strain curve for cold rolled steel is a bit higher, and that's because of the cold forming effects. By definition, light gauge steel is a thin walled steel that is manufactured by a cold rolling process. So we'll have a look at that later on in some of the videos. Note that they have a galvanized coating, so that that's protecting from rust, and I believe the design life is something about 50 years. And the term cold is because the steel profiles, as we see, are going to be rolled at room temperature. So here's the difference between cold rolled and hot rolled steel. Production temperature, as we said, is going to be done at room temperature. The grade that can be up to 1000 megapascals, so a bit higher than hot rolled steel. It's got low to medium ductility, so the ductility is not quite as good as the heavy steel. The weight is light, which means that people can carry it. Section geometries can be rolled into almost any shape that you like, and it's got dimensional accuracy. So cold form steel is thin walled, so the thickness of the profiles is about 0.5 millimeters to 3 millimeters, and it's designed by either press braking or roll forming. So right here you'll see this is pressing, so this is all done at room temperature, and you're pressing the profile into a shape, and then down here you'll see the rolling through a series of rollers that form convert the coil into the shape that you want, normally channel sections. So it's exactly the same type of section or steel that's used for the cars. So if you think of a car, it's quite thin in terms of the steel, and that's exactly the same. And these days we're looking at applications of cold form steel to pallet racking systems, which you can see here. You can see some houses, which you can see here, and you can see some flooring systems, which you can see down there. So those are the general applications of cold form steel. So having a look at this video down here, you can see the sheet metal is coming through the rollers. So it's coming through the rollers and then it's pressed into shape. Down here, that's another picture of the press braking, which is done at room temperature to change the shape from the flat into an angle section. And then down here, you can see a top hat batten section, which again is pressed at room temperature. So the key thing is everything's done at room temperature, and with this, you can typically get up to the 6 meters. Here's a video of the roll forming process, which is different from press braking in that you've got a series of machines or rollers which turn the profile into the desired shape. So as I said, normally some variant on the channel section. So manufacturing of standard profiles and panels, which you can see in the video down here. And again, for these sections, you can roll a coil of more than about 1 meter wide and about 1000 meters long. So here's a video taken from one of the New Zealand manufacturers. So down here you can see that the coil is fed into a machine, so a bit like a car. You can see that the holes are being cut, or the holes in the sections are being cut as the profile moves through them. Through a system of rolling machines, you can see from the flat shape right at the start, you can see how it's turned into the final channel section at the end, and then that pops out right here. So it's a very, very mechanical and automated process. And when I mentioned New Zealand at the start of the lecture, most of the major manufacturers of these machines or these systems are actually based in New Zealand. So I'll just quickly scroll through the rest of the video, and you can see some of the profiles that can be made from these sections. So there's an organization in New Zealand and also in Australia, and it's called NASH. So if you wanted some information later on, please just Google NASH, and you'll be able to find out some of their information about the rolling machines and what can be manufactured by the New Zealand industry. So these are the typical profiles. So I've been mentioning that they're channel sections mainly. So you can see these channel sections through here. C profiles, Z profiles, typically used for the purlins in portal frame structures, and then some top hat sections which you can see down here. And in terms of panels, flooring and roof decks, long composite span decks. So if you think of a composite floor system, that's also made from coat form steel, rib panels and corrugated sheets. So these are the typical profiles that can be rowed using coat form steel. So the most conventional sections are the C section. So you can see the C section down here. So as we know, of course, the shear center of a C section is outside the shape, and the center of gravity is there. So these sections, they're pretty, they don't really have much resistance to torsion. So you do need to have some pretty clever details to stop the twisting action of the sections. Z sections, which we see up here, that's very popular for purlin sections. So we can see the purlin shapes. Typically these are used in UK on the roofs of portal frame sheds and other things. And then we can see they don't really experience the eccentricity of the loading, as the shear center is pretty much at the same position as the center of gravity. And they also nest together quite well in splices. Some new profiles that have been developed in New Zealand. So this is a box section, which you can see here. And then there's a seam locking system, which you can see up there. So we've got the box section, which would start off like that, gradually move it together, and then a seam lock which would appear up there. So the particular company is called Futura.nz, who manufacture these profiles in New Zealand. And here's a video of the Futura line. So you can see these sections are rowed, they're put together, can be put straight into a truck or a lorry, and then moved to site. And in this case here, the sections become the portal frame column and rafter members, as you can see there. Now, in order to design, or in order to understand the behavior of cold form steel sections, it's quite useful to know what the imperfections are. So at the universities, we have laser scanners, which you can see here. So we would be typically laser scanning these profiles in order so that we can have an understanding of their geometrical outer plate plumbness. And then from there, we could put it into some finer element software. We'll see later on. With cold form steel sections, these days having openings is very important. So you can see openings here for the surfaces to be run through. Clearly, if you punch a hole in a cold form steel profile, you're going to be decreasing its strength here. So some of the recent work that we've been doing at the university is looking at these edge stiffeners. So maybe you can see an edge stiffener around the hole here, and that pretty much means that you almost restore the strength. So if we look at this graph here of axial load against shortening, this one here would be the section without the hole. As I said, you put a hole in for the surfaces and it reduces the strength. But if you have an edge stiffened hole around here, you can actually see that it's actually got a strength enhancement over the no hole case. So that's some of the work that we've been doing. Some other work that we've been doing is for roofing profiles. So here you can see a roofing typically used in houses in New Zealand, and then we'll be doing some pressure or suction tests, pretty much looking at how the screws fail in these members under cyclonic loads. So right here you can see one of the tests that's been done at the university, and as I said, we're sucking and pushing the air back into it, and then looking at the failure of the screw at the end of, say, 1,000 cycles. We've also been looking at full scale portal frames, again with box sections. So this is another system by Vertibeam, which you can see here. And in this particular case, we're using welds here and here to weld two C sections together. And then that forms another box section that can be used for the New Zealand market. I should mention that the New Zealand market is in New Zealand, it's very important of hygiene. These factories or these buildings are normally used in the agricultural industry. So we're looking for cleanness of the lines. so that birds and other stuff, don't perch on them. And down here you can see the details of the box sections, which would become the portal frames. And here's some other testing that we've done at the university. So this is the box section, which we can see here, and around here we can see that we've been loading it under vertical loads. So down here you can see these are water canisters that have been filled up with water for the gravity load test, and we would also have done a cyclic test. And this one would be the cyclic test that we did on that, and you can see the failure down here in terms of how the profile failed under the cyclic loads. And the hinge, if you like to call it, would have been formed there. You can see the profile is tapered. And then down here you can see how it failed under the gravity load. Down here you can see the buckling of the portal frame. So the failure mode down here, almost a bit like elephant's foot, I suppose. Another use of coat-formed steel sections in New Zealand is the pallet racking systems. So these are freestanding structures, and they're less expensive than conventional steel racks, and they're used within warehouses. Down here we can see some other videos that have been done in New Zealand. So we've got a pullback test or a snapback test, and then from there you can see the behavior of the racking system under controlled rocking. So in New Zealand, most of the portal frames most of the coat from steel is used in portal frames. So it's a very, very large industry. In the UK, it's a large industry as well, but many countries would be using other systems, like the US would be using concrete for single-story sheds. Problems with portal frames in coat from steel: excessive deflections because the members are thin. We've looked at the cladding as well. Cladding and fixing damage can lead to water penetrating the building, which of course shouldn't happen. Ponding of water on low pitch buildings, and then objectionable sags in the rafters or the suspended ceilings. So these are some of the systems for portal frames. So you can see a brace down here, and you can see here a moment joint. So part of the problem with coat formed steel is that these joints, which you can see here and here, the joints can be semi-rigid, so different from hot rolled or heavy steel, where welding can take care of that and you can effectively have a rigid joint. So part of the problem with coat formed steel design is how to take into account the semi-rigidity of the joints. So this is a paper that some of the work has been presented in terms of the joint testing. So you can see load is coming onto the joint one channel section here and another channel section here, and you can see a plate or a gusset plate which here, and then the two channel sections on either side, you can see they've been bolted or screwed through to the plate, forming your moment resisting joint. And obviously that does have some flexibility. So here we see how the joint is formed. So we can see that it's a combination of screws and bolts. So the screws are basically just to hold everything in place until the bolts go through. But in terms of the experimental testing, we actually showed that the screws carried most of the load. So in this figure here, we can see the test. So you can see the test video. As the load is applied, suddenly the section pops out or buckles in the outer plane direction. This other member here, that would be the eaves beam in the portal frame, providing some restraint. So as we mentioned right at the start, channel sections have a tendency to want to buckle in torsion. So you can see two channel sections here, which have been connected through the gusset plate here, and indeed as the load is applied to the system, there's outer plane buckling, and you can see the outer plane buckling occurring perhaps a bit better in this picture here. And then this has been modeled using finite element modeling, as you can see in the video right at the top. Here are the load displacement curves. So as I mentioned, it's very important with coat from steel to know what the stiffness is. so the stiffness can only be measured through an experimental test. We can see that there are some equations from the literature that can be used to predict the load displacement of the bolts or screws modeled in a finite element model by connector elements, and there's an equation that you can get there from the literature. So if you're familiar with finite element modeling, it's not too difficult to set these up, but it's more important to know what the load displacement curve is of the fasteners, and this equation will give that to you, and you can see that can be modeled down there. So right down here, we can see where the two screws failed in the test. So in both tests, in the first test, the first and second screw failed at the same time, and in the second test, the first screw failed, drop in load, and then the second screw failed. So with the finite element model, we could actually say what happens if there were more screws or the screws didn't fail, and then we can predict an upper bound to the failure. And if you wanted to, you could use some equations to calculate the rotational stiffness of the portal frame joint. So some other tests have been done in the literature. So this is a full-scale test that's been done before, and again using the finite element models, and from the laboratory test results, you can see that there is a variation in terms of the stiffness of the joint. So in this particular case, two portal frames were tested. One frame had a smaller joint, that's the eaves and the apex joint, and the second frame, which had a larger eaves joint and a larger apex joint. So the frame with the larger joint has a larger stiffness, and the frame with the smaller joint is more flexible or has a lower stiffness. So you can see from this graph quite clearly, which is load against displacement. That's the displacement there, and that's the load that's been applied through this jacking system. You can see how important it is to get the joint detail right if you're trying to avoid damage of fastening or ponding of water into the system. And again, finite element modeling and a beam model that designers can use in a design office. Here's some pictures showing the mode of failure of the boulder connections, and then this leads to wondering how these structures behave in fire. So this is some work done with Professor Sonaby and his PhD student Ross Johnson. So what we did, we designed a portal frame, and it was actually tested in Malaysia under fire, and then down here you can see the failure of the system. And of course, with finite element modeling, you're able to quite accurately predict how the building actually performs in fire, and you're able to predict the temperature at which the apex joint would fail. So we can probably see in these figures that there's quite a good match between the finite element models and the experimental test results. And of course, more details can be found in this paper here. Just contact Professor Sonaby, and I'm sure that he can pass it on to you. So that ends the presentation on cold form steel. So I've covered quite a few different systems, mainly portal frames in New Zealand, but also houses as well. So there's a big housing industry in using New Zealand technology, but more in Australia, US, and other countries where they're using this particular form of construction for houses, much the same way that you would be setting up a car manufacturing system. So the normal question is, why can't you use the same type of steel as you would use for cars for housing? So if you've got any questions, feel free to drop me an email. My email address is james.lim@auckland.ac.nz, and I'll be very happy to take any questions later.